Hi everyone, welcome back. So we all know square root of negative 1 is denoted by complex unit I. What about square root of I? Can we find out square root of I as well? Answer is yes, we can find out square root of any kind of complex number. We know that I is an imaginary unit, so if we put square root on I, we will most certainly end up with a complex number. So most probably square root of I is going to be another complex number. Let's try solving it. There are two ways of solving it. We'll start with method one, that is by using standard algebra. And square root of I is going to be another complex number. So it can be expressed in a standard form a plus ib. First and foremost thing, we are going to solve it by simply squaring both sides. Squaring to the left side, square root of I, if we square it, we will simply get I. And in the right side, we will get a plus ib whole squared. And if we use simple formula to square it, we will get square of the first term a square plus twice of product of both the terms 2ab into I, this is plus, and last term will be square of the second term, that is b square multiplied by I square. We already know that I square is negative 1, so we get I equals to a square plus twice of ab into I minus b square. I square is negative 1, so it becomes negative of b square. And this is twice of ab into I. What we can do here is that we can put both real terms together so that we have coherent looking equation. I equals to a square minus b square plus twice of ab into I. This is what we are getting. In the left hand side, we have a complex number iota, and in the right hand side, we have another complex number. Both LHS and RHS will be equal if their real parts as well as imaginary parts are equal. So left hand side can be written as 0 plus 1 into iota. And right hand side, we already know it is a square minus b square. This is b square plus twice of AB into I. If we equate real parts from LHS and RHS and imaginary parts from LHS and RHS, we will get something like this. A square minus B square equals to 0, and twice of AB equals to 1. Twice of AB equals to 1. These are the two simultaneous equations that we are getting. We can very easily solve these simultaneous equations to get the values of a and b. Let's start from the second equation. Twice of ab equals to 1. So I can get b equals to 1 over 2a. And we can substitute this value of b in the first equation. We get a square equals to b square. B square is basically 1 over 4a squared, right? So we can transfer a square to the left side and we get a raised to the power 4 equals to 1 over 4. And if a raised to the power 4 is 1 over 4, we will get a square equals to either plus half or negative half. We know that a and b both are real numbers, so a square cannot be negative half. Let me write that. Yeah, a square equals to plus half, a square equals to minus half. These are the two answers that we are getting, but obviously we have to ignore this a square equals to negative half part, because a square of a real number is never going to be negative half. A square of a number can be negative half, but that number has to be a complex number. So we are getting a square equals to half. That is, we are getting two values of a. One is 1 over root 2, positive 1 over root 2, and other value is a equals to negative 1 over root 2. These are the two values that we are getting. This one was 1 over root 2, right? And if you remember, b was nothing but 1 upon 2a, 1 over 2a. This was the value of b. We can calculate value of b from here very easily. we will get 1 over 2a. If you simplify it, you will simply get 1 upon square root of 2. Same as value of a. And similarly here, if you evaluate the value of b by using 1 upon 2a, you will again get negative 1 by root 2. Negative 1 by root 2. So these are the two pair of values of a and b that we are getting. So the square root of I can take two forms or can result in two complex numbers. One complex number is obtained by taking the first pair of values of a and b, that is 1 by root 2 and 1 by root 2. Second complex number is obtained by the second pair of values of a and b, that is negative 1 by root 2 and negative 1 by root 2. So I can say that square root of I is basically plus minus 1 over square root of 2 plus 1 over square root of t 2 multiplied by iota. These are the two values of square root of I that we are getting. We have to note one very important thing here, that if we calculate square root of real numbers like square root of 4, we get only one answer, that is 2. Never mistake it for plus minus 2. Square root of 4 is always 2. Similarly, if we try to calculate square root of negative 16, negative 16 is also a real number. Square root of negative 16 is again 4 iota, 4i. It is never going to be plus minus 4i. So square root of real numbers always result in single answer, but square root of complex numbers can have multiple answers like we are seeing here. This was one method of evaluating square root of I. Let's try another method by using Euler's formula. We know that every complex number can be expressed using Euler's formula as z equals to r multiplied by e raised to the power I theta, where theta is the argument of the complex number and r is the magnitude of that complex number or length of the vector corresponding to the complex number. We are not going to discuss these terms in this particular video. I'll make another video for that. But for now, we can use this idea. We know that complex number I can be written as e raised to the power I pi by 2. There is one more thing that we must remember here, that if we plot a complex number on xy plane, two-dimensional plane, let's say I have a complex number z. This complex number z can be written as r into e raised to the power I theta, and theta is the argument, this angle from the real axis, that is x-axis. Now what happens if I rotate this complex number by 360 degrees? You will notice that we will reach to the same point from where we started. And if we rotate it another 360 degrees, then again we will reach the same point. So the basic idea is that if my complex number iota can be written as e raised to the power I into pi by 2, this angle pi by 2 can be written as in a general form by adding multiples of 360 degrees, that is 2n pi. Right? So if we add 360 degree here, still we will get the same complex number. If we add 360 into 2, we will still get the same complex number. And we are going to use this idea to calculate square root of I. Now we don't have to do much, just take square root on both sides and we will get square root of I equals to e raised to the power I times pi by 2, this is pi by 2, plus 2n pi raised to the power half. So if we take power half of this whole expression, we basically what we will get is that half will get multiplied with this exponent. Half will get multiplied with the exponent of e raised to the power I theta. So what do we get from here is that e raised to the power I times half will get multiplied and we get pi by 4 plus n pi. This is what we are getting. And I think I forgot to say this before, n is integer. So we can take any integral value of n. We can take n equals to 0, n equals to 1, n equals to 2, n equals to 3, or negative values as well. So to calculate square root of I, we just have to substitute the values of n, and when we substitute n equals to 0, we get square root of I equals to e raised to the power I times pi by 4, and the second term will simply become 0. Right? This is what we are getting. If you calculate this, you will get the first answer that we got from method number 1, because e raised to the power I into pi by 4 can be written as cos pi by 4, cosine of pi by 4, plus imaginary number I times sine of pi by 4. And when we evaluate these two numbers, we will get a result as before. 1 by root 2 plus 1 by root 2 multiplied by imaginary unit I. Right? This is what we have. Similarly, if you substitute n equals to 1, we will get the second part of the answer that we got from the first method. Square root of I will be negative of this expression that we have written here. 1 by root 2 plus 1 by root 2 multiplied by I. These are the two values that we are getting for square root of I. Now, what happens if we substitute higher values of n or lower values of n? You can try it as homework. What you will get is that since we have only two unique values for square root of I, the remaining answers that we will be getting will be just a repetition of these values. And why are we getting repetition of these values? Because this idea that we discussed, that upon adding 360-degree complex number, you are reaching to the same point from where you started. So these are the only two unique answers that we get. I hope both these methods were clear to all of you. And if you like the video, don't forget to subscribe the channel and share the video with your friends. Thank you very much for watching. Have a very nice time. Namaste.